The last video of chapter 22, we're looking at HPLC, which we'll see in a second stands for high performance liquid chromatography. So it's a different class of instrument than the gas chromatography instrument. So HPLC is the abbreviation, and it stands for high performance liquid chromatography. At one point, it was called high pressure liquid chromatography, but it's not anymore because they don't have to be at quite the high pressures it used to be. Plus, now they're all about performance. So anyway, what happens is in HPLC, we use this when we have samples that that are not volatile enough for the GC. So we're not able to boil them at the temperatures we need to. Because for gas chromatography, it has the solvent. Oh my gosh, words. The sample has to be in the gas state for it to work. So this is what we use. HPLC is used for aqueous solutions. Okay, so because they're things that aren't easy to boil. Okay. So what happens in this is we have and I think I'm gonna say this, or I'm gonna say it right here. The stationary phase is a packed column. So it's using typically adsorption chromatography, but it could be ion exchange, it could be molecular exclusion, but a packed column. And so the stationary phase is a solid, and the mobile phase is going to be a liquid, and that liquid will be whatever the solvent is, and at the same time it can vary throughout the course of the experiment. Like it might be that it's 60% acetic acid, 40% sodium acetate is the mobile phase, and then as the experiment moves on, they have the computer set up to vary it to where it subtly shifts to become 100% acetic acid or something. But that'll be for you instrumental analysis people to deal with. This is an old school picture, because I mean, look at that computer, friends, of HPLC. So just imagine a computer. The rest of this instrument looks the same. This is typically sitting on top. So it's kind of like a three-part column or three-part, I cannot words, just real tall thing. Okay, so what happens? Two of the parts are pumps. That's to get the pressure to force it through, because what happens with HPLC is we're using aqueous solutions, and they go real slow when they flow through things. Okay, we have gravity on our side for this because we'll have the column set up, the packed column set up, so that way it flows down, but at the same time, water goes very slowly through a packed column. So these are the pumps that are able to put pressure on it to force the liquid through the column faster. This is the column right here. I said it's a little bit longer than like a pencil. Okay, it's narrow. And then, so the injection port is right here. So we're going to be using a syringe, just like we were for gas chromatography, to enter a sample. The sample, these pumps then push on the sample to force it through the column, and then it goes into the detector. The most common detector, and we're going to talk about it later, is an ultraviolet detector. So we end up with answers that are absorbance. So it has to be a compound that measures ultraviolet light if we have this type of detector. Okay, so columns. Patch column. But it's very short because of that diffusion. It has to be very short. And we need to do the best that we can to make sure the size of the stationary phase particles are small and consistent. Okay, so this is kind of giving you kind of a view of what these columns look like from the outside. Like I said, about the size of a little bit longer than a pencil, maybe a little bit wider than a pencil. These columns are expensive for being as small as they are, and they have to be kept closed because we can't let dust and debris get inside of them, because then that's going to stick onto the stationary phase and cause problems. So these columns, they're very expensive. We're talking, like $800 to like $1,500 a piece. And they last for a while, and even if you take amazing care of them, they will eventually need tossed out, and you'll have to buy a new one because dust gets in them, impurities get in them, they get used too much to the point where the surface of the stationary phase is starting to degrade. All kinds of things can happen. So the stationary phase is typically made of silica and small beads, and most of them are pH sensitive. So like you can't have the mobile phase be above pH 8, because what happens is the stationary phase will dissolve. Okay, so in real life, you would buy the column for what you need, and you would know the limitations for it. So the surface of the stationary phase, so it's the silica. So it's this silicon with oxygens and hydrogens. So this is like the things sticking out. Okay, the things sticking out off the surface of the stationary phase. Little, I think of them as little beads because that's usually what they are, little spheres, little tiny beads. Okay, so in the solution process, again, adsorption chromatography is the way this works. The solvent molecules are the mobile phase, and they are also interacting with the stationary phase beads. And so what happens is the solvent will constantly push the solute, the sample that you're testing, down the column. Partially it's because of the pressure pushing it down, but it's also because it's interacting with it. So when we're looking at HPLC, and I'm gonna give you some definitions here in just a second, but it's all gonna be about polarity because it's adsorption. So we're gonna have the stationary phase and the mobile phase. One of them will be more polar than the other, but usually both of them have they're at least partially polar. We're not gonna have one that is completely nonpolar, and so that elution is all based on those intermolecular forces. So the types of chromatography. What is called normal phase, and this is again for HPLC specific, normal phase chromatography for HPLC is that the stationary phase is polar and the solvent, the mobile phase, it says less polar, so closer to being nonpolar. Okay. Now, reversed phase chromatography, which is more common. Yeah, think about that. They called the other one normal phase chromatography. The reversed phase chromatography is more common, and that is true. But reverse phase chromatography, and there should be a Y right there. Ba-bam, ba-bam. Okay. Is when the stationary phase is less polar and the mobile phase is more polar. And the reason why that's most common is if we're talking about aqueous solutions, our mobile phase is going to be water, and water is very polar. Okay. So, know these two definitions, I guess. Know which one is more common, what the definitions are. So when we're looking at this elution process, the blue semicircle with the triangles on it is the stationary phase. Okay. And then the white squares are the solvent and then the sample. Okay. So what happens is the sample will adsorb to the stationary phase. So I lied. The light blue is the stationary phase. The dark blue triangles are the sample. So it sticks to the stationary phase because it's got intermolecular attractions to it. Now the solvent, which is a solution but has a high pressure behind it, is being shoved down. What it's going to do is it's going to knock the sample out because otherwise it's just going to stay stuck to the stationary phase. So the solvents, the mobile phase's job is to help keep the sample moving so it doesn't get stuck on the stationary phase. Okay, a couple more definitions. Well, these two definitions, and we have to talk about detectors really quick. So definition of isocratic elution is when you have whatever your mobile phase is, it's the same chemical the whole time. Whatever it is, it's always the same chemical. Gradient elution is when your mobile phase is a mixture of two solvents, and that mixture, like the percentage of them, varies over the course of the experiment. And so this will make more sense for any of you going on into into instrumental analysis, but know the terms. Isocratic elution means we just have one mobile phase, same concentration the whole time. Gradient elution, we have two mobile phases we're making a mixture of them, and then we change the concentration of the mixture over the course of the experiment. So last thing is talking about the detectors. So the most common detector is a spectrophotometric ultraviolet detector. So it's like xenon flash lamp inside of the UV. Instead of there being a cuvette, after it comes out of the column, it's run through a clear, it's the cuvette is basically like a little tube that the sample is running through, and the light is shining at it. So it works just like a spectrophotometric, like a photomultiplier tube detector. It's just, we've got a light source, we've got a monochromator. It's just the cuvette part is different. That's the most common one. That's the one that we have. We have an HPLC. It doesn't work right now because of the dumb pumps, but we have one. Electrochemical detector is an option when we're looking at things that can be oxidized and reduced, and so it measures the potential compared to a silver chloride electrode. So basically it is doing a cathode minus anode calculation. And then the third one is evaporative light scattering, and this is with something that, I mean, we're shining light at it, and it's based on the way that that light interacts. Okay, that one is still a thing to know, but not the, again, spectrophotometric is the most common with UV light source. So that takes us through some generic things for HPLC. There's more information in the textbook. This is as deep as I want you to go. We're kind of doing a narrow, we're not going too deep into this chapter. We're hitting the highlights, we're learning some important words and getting a little bit of understanding behind the instrument, but not the deep dive.